be homework assignments that you can use on Stellar to submit when you're ready. And because the individual, you don't need to wait the last day of April to start filling it in. So hopefully that's an advantage to be able to start whenever you guys want. The presentations, let's just, because this is always acting these days. It's probably my laptop. March 7th, we'll start the presentation. So you essentially get 3 days without anything in class here. The last lecture is March 1st. And then the presentation starts on March 7th. And the requirement there is to listening to 20 of those presentations. There's going to be 46, so you'll have options to choose from. Professor Eager is working to try to make it more than 1 hour long each time. And I don't know exactly how that's going to work out, but one idea is to start a little earlier, like 8:30, or go a little later. But I'm not going to say which way exactly it's going to go. With respect to how to prepare for the presentation, you should talk to us. You know, if you have any progress made, you know, you have some ideas of what you want to work on, but you know, there's nothing wrong with verbalizing a little bit via email or a meeting, just saying, you know, this is what I'm thinking about. Do you have any comments? Or you can even start working on a draft presentation. There's nothing wrong with sending it just for feedback. It's not that we're going to go through the details, but we may tell you, well, you know, maybe you want to go a little deeper into this, or maybe you want to give a little bit of an overview. So there's been, over the past year or so, a little bit of a tendency for you guys to wait a little too much last minute to put it together. And that's probably the caution I want to give you, to get started early. The idea is to pick something that you're interested in, you don't know everything about, but you want to learn. And, you know, just take it from there. As far as today, we're going to go over, essentially finish up on material specifications, and then move on to a little bit more of a failure analysis at the end. I have a case study that I want to talk about. One thing that we've talked about a few times already this semester is a lot of times you do end up having to join materials. So in the context of steel, in addition to being not expensive, you can weld steel and maintain approximately the same property. So it's a big advantage. And, you know, the simplest example is a chain. If you want to make a chain, you have to weld the material. So you can think of trying to make a chain that is super, super strong, but a lot of times the highest strength steels are harder to weld. So there's always a practical limit that you go through. And this one is a magnesium-based chain, so it's very, very light. And magnesium is a little harder to weld, and you'll see it on the quality of the chain itself. So this one, very lightweight. I wouldn't, you know, bet too much on the fatigue resistance just by looking at the welds. There's some porosity. This one is coated because you want to get some corrosion resistance a lot of times. The problem with coating is where the links of the chain meet, you'll wear out the coating a lot of times. So if this is a very, like you use these for offshore platforms for oil and gas, for example, where they can be tethering. So you have a buoyancy can that's holding the entire structure down at the bottom of the sea, and it's held in tension. So it's in a corrosive environment, and everything that goes there is very expensive. So you do try to get higher strength steel. The chain links. I have a case study that hopefully I'll show next time tomorrow, and essentially you design for the material, its cost and all this, but when it comes to joining and protection, it all comes together to help you make a decision. I mean, it's never easy to decide if you have a new application, which material is best, because it's very, very rare that you only have one parameter that you're trying to optimize. Cost is always there, but the performance, the transportation. When we were talking a little bit about wind turbines, they can be very lightweight and very inexpensive, but then you have to bring them to the site and install them. So a lot of times, if you can make them in modules, for example, to transport them by trucks, that becomes another requirement. You're limited by the size that you can put on the roadway a lot of times. And they're trying to get away with some of that. If you're building up a new bridge, for example, a lot of times now they'll put up a concrete plant, a temporary concrete plant just next to the bridge to save in transportation and be able to make heavier, bigger segments than what you could put on the regular road. They try to do that also for if you have a new power plant that you're putting together and somebody wants to have this huge turbine. The idea, again, is instead of trying to make it somewhere and try to transport it, if you can make it on site, you definitely save on transportation. Now, are you going to be able to use the same processes than you would use in a very advanced factory? Maybe not. So this is where reality checks in, and you have to decide how much you care about the transportation aspect versus the actual properties of the casting or the forging or what you're trying to put together. It's more common with castings than forging. It's getting more common to have sun fabrication on sites. I brought in earlier in the class an I-beam that you can make from plates. So if you're having a little bit of a custom construction, you can bring that in and just do everything more on sites using standard shapes than trying to have an inventory of more raw material for the fabrication becomes a criteria there. Having a lot of trouble with this, and it's not fun. there. If I didn't have that much visual, I wouldn't care. Let's see what we have. We have a lot of visual. Anybody has the adapter? I have one downstairs too. HDMI to VGA, I believe.
Probably Thunderbolt to any of these three. I don't know if you have that type of connector. But do you have that in here?
Let's see. I don't think so. No, HDMI is really, yeah.
Sorry about that.
No, thank you for. Is that looks exactly like mine? Thank you. I'll try to make sure I don't run with it. Don't know why. Yeah, but I don't know why straight HDMI doesn't work. It seems like a screw-up way to do it. Okay. Thank you. All right. So what we were saying is we'll finish the processing and product specification. Tomorrow we'll talk more about factors of safety. And what I've tried to do was to blend in a lot of failure analysis through the lectures. So what we're going to do on Friday is go specifically, and I'll bring some fracture surfaces for you to get a little bit of a sense of how that is. But hopefully the general topic of failure analysis got through the lecture in general. This semester I'm doing 8 lectures, so for the remaining 4, I give you 4 or 5 different options of different things you can look for if you're interested more in welding, corrosion. There's a section on plastic and composites that may be interesting. And if you have anything in mind that is not here, you can do that as well. There's no real, if you say, oh, I'm going to just do a few lectures on welding from Dr. Eager, that's perfectly fine. We touched last time about different designation, and the AISI SAE was one of them. We talked about a 1020 steel, a 4130 steel, being essentially speaking to the chemistry. So how much carbon there is in it. It doesn't even have really requirements for maximum impurities. So it's really just for alloying elements. If you want a little bit of chrome in there, HSLA steel, for example, that will come into this chemistry designation. But if you remember, we said if you go to an ASTM standard, a lot of time it's more robust because it will include requirements for mechanical properties, some maximum of the impurities. It will tell you to calculate a carbon equivalent, so it's weldable if you want a weldable grade. So there's just a lot more information and usefulness that you can get out of a performance-based specification. But it's good to know the chemistry specification. We went over it for the aluminum alloys. It's 4 digits For a wrought product, 3-digit with a dot on a casting. And this page for the aluminum association designation may be useful to you. So if it says F after the chemistry, it means as fabricated. O is for annealed. You could be hardened. These are the 3000 and 5000 series alloys. And then if you have a heat-treated grade, a lot of times it will have a T there and either 2 or 4 digits after that. So you know a little bit what you're looking at. If I have a 6061 T6, for example, which is very, very common, it means when I'm going to weld it, I will lose a lot of that heat treatment. And that's why for some applications, if you're thinking about performance bolts to go on the ocean, they'll tend to be 5000 series aluminum without the heat treatment, and part of it is the corrosion resistance, and part of it is there's so much welding involved that it wouldn't matter. If you try to use a higher strength, you're only going to get the strength of the weld metal. We didn't go too much over the different heat treatment. T6 is the peak aging, but there are situations, if you have rivets, for example, to build an aircraft fuselage, it's very interesting how a lot of them work. You do the solution treatment, so you heat them up and quench them, and then you keep them in the freezer so they don't become harder. In other words, at ambient temperature, they will age and become harder. There's going to be a dispersion of precipitate forming, and to delay that, you keep them in the freezer, you install them in just the strain of deforming activate this transformation of forming precipitate. So within an hour after installing the rivet, it could be as much as twice as strong in terms of yield strength than beforehand. And so you take advantage of the low yield strength for formability, and then it gets harder from the action of work hardening, but mostly the formation of the precipitates at the higher temperature, and it is improved by the deformation. So essentially creating all these dislocation network during deformation helps with the formation of higher strength precipitates for hardening by precipitation. I mentioned earlier that I was going to talk about pipelines, and it fits very well in the context of specifications. So in the US, you see the red, these are liquid transmission pipelines that go between states. And in blue, you have the gas transmission lines. So these are all typically 45 centimeter or 1.5 feet and above in diameter, and they're used at high pressure, so hundreds of PSI. For transportation between where we produce natural gas, oil, or crude, and where we use it. It's a lot, if going across the country is 3,000 miles, then you do that 100 times is how many transmission pipelines we have. And if you include distribution, which means everything in Massachusetts to bring natural gas to Cape Cod and everywhere that we want it, you're talking about 2 million miles. So it's an incredible amount. Most of what is in transmission pipelines is still steel. When you go to distribution, since the 1980s, we're mostly using HDPE, so high density polyethylene. So with respect to the pipes, it's a specification from the American Petroleum Institute that is most widely used. It does include what we call material requirements, so chemistry, It has some processing requirements, performance requirement, and quality control. And it has changed a lot over the past 80 years. And that speaks to one thing I said, that it's very difficult to start a new product from scratch. Saying I'm going to design this without taking into account other things that are out there, because there's a lot of history and trial and error to get a standard that, well, first of all, everybody understands, that everybody can use, not only have the methods. Like, what happens a lot with making standards for materials is you have to get together the users and the manufacturers, because I can be there as a design engineer saying, well, I'd like my my pipe to not have any welds, for example. And the manufacturers say, well, I could do that for you, but there's going to be a lot of limitations. I'm not going to be able to have a good tolerance on wall thickness. So if you have a seamless pipe, it means that you really are extruding out the inside from a billet, and the end product is just very, very hard to maintain a good wall thickness tolerance. So, and it's more expensive. So the people have to get together, and this is a big example again for the industry because of the amount of steel and how critical it is. And I posted it on Stellar, just so if you want to get a sense, like an example of specification. We won't go through the details, but you can see here, it will tell you a little bit about different ways you can do a cold expansion. You may or may not have a heat treatment. So one of the difficulties with a specification like this is a lot of times it will give you a lot of options. So it's not clear if you're the user that you're getting exactly what you want if you don't put additional requirements. So the specification here will give you so many ways that you can do the welds. So one thing that we didn't talk about is these pipes for cost purposes. I mentioned about seamless, but the majority of them, maybe 90% of them, are done from a flat sheet that you roll, and then you have a longitudinal welded seam all along. Yes?
Did you say they're now made of high-density polyethylene?
No, so this one is for steel. So this is for transmission pipelines. The high-density polyethylene is for distribution. So we're not, yes.
There's distribution and there's
Transmission. Transmission is essentially between states, more or less. It's higher pressure is how they define it, and then distribution is more within state when you go from the major hub. So there's only going to be one transmission port in the region, and then it gets distributed using smaller pressure lines.
And so is that because the steel is cheaper than the high-density polyethylene?
That's a very good question. So for the videos, the question was, why are we using steel for transmission? And it's higher pressure. So if you wanted to try to get this level of pressure with a plastic, first of all, the wall thickness would have to be very, very significant. So in terms of joining and just the practicality of putting it together, it's not worth it. I can't exactly speak to the risk, but I think that there's also an aspect of experience with steel that we can look for cracks. We have so many tools. There's a lot of inline inspection tools that run through the pipelines as you transport the fluid and are doing monitoring. They're looking for small cracks. They're looking for wall thickness reduction, because it's so critical. It's such a high pressure that if you had tomorrow to develop that type of technology for high-density plastic pipe, it will take a long time. So there's definitely more inertia, just a little bit like when we talked about airframes, in making a change that's significant, because not only you need to change the process, the quality control, but then the field inspection techniques for it.
So it's transmission is interstate, distribution is in-state.
Yeah, it's a simplified way. So the transmission is essentially high pressure, and distribution is a lower pressure. Going back to specification per se, you see they will talk about couplings, inspection, so you have a hydrostatic test that needs to be done on those pipes. There's a certain amount of dimensional control. So all these things that you could say, I'm going to just say what I want, is built into the specification to some extent. So again, there will be options on grades. So if I have an API, what we're going over right now is API 5L, there will be different strength levels listed in there, and there will be different type of coupling that you can use that you have to specify exactly what you're looking for. And the document is 166 pages. So, you know, that's why doing a detailed design can take a long time, because before you decide whether you want to use that API standard or an ASTM standard or come up with your own specification, you kind of have to go through what's in there. They will tell you a lot in general about what they're trying to do with the standard. So this is, a lot of times I find it very, very useful to just read the first paragraph, because it contains more information that you will think. So here it says, for example, we cover seamless and welded steel line pipe. Okay, so it means that when I call for that standard, I don't know if I'm getting seamless or welded. It means I have to determine that. I have to tell them if I have a preference, because the standard is for both. There will be standards sometimes that are more specific. There'll be standard that will say specifically, well, this one is for seamless, so you don't have to specify it. But in the case of API, it's often the case that there's a lot of flexibility in the general standard. Now they're talking about quality levels, and here's the discussion about grade. And it's a little bit distressing, I guess, to think that the same specification is going to give me the A and B grade. So some of those would be only, and I'm sorry, this is the specification, so it's all in PSI and KSI. So the grades there are in thousands of PSI. So the lowest grade you have for those steels is 28,000 PSI. The 42,000 is very, very common, and then that's what they call the X42 there. And then the more modern steel, if you're putting a pipe in the ground right now, you could be looking at an X65 or something like that. The trouble as you go to 65 is how you're going to weld it and still maintain the same properties. So the same issue comes over and over again. And that's why a tight control over chemistry becomes important. I had a discussion yesterday on this, essentially saying, well, sometime we'll ask for the X65 steel, which sounds like a good idea, so I can have a better usage of the steel, use a higher pressure for a certain wall thickness. But depending on the detail of the chemistry, when you weld it, it will soften. Why does it soften? Is instead the mills decide that instead of investing in chemistry, they do a little bit of a cold forming of the steel to be able to meet the specification, but it's not helping with respect to the as-built properties. And there's nothing in the specification that says you're not allowed to cold form. You could add that. You could say, I want an API 5L pipe that is normalized. Great. So you know you're not going to have this cold forming. But if you, it's really, I hope that this hour or so that we spent on this makes you think that if you don't ask for it, you may not get it. You may be lucky to have somebody that's going to think ahead and understand your application and what you're trying to do, but a lot of times it won't happen. Yes?
What is a full specification?
A full specification for a material or a design?
Material with properties. So I guess design is one thing, and with the drawing.
Yeah.
Specify on that drawing the material type.
Yes. Yes.
Okay.
It's a very good question. So if I tried to do detailed, like I'm trying to be very careful in specifying a material. I have the drawing that says this is my tank, and you have a little note that says the material. Coating is just completely different than the material. But with respect to the material, on the drawing, a lot of times you'll have a designation that will say ASTM, certain grade, certain chemistry perhaps, because you can include the chemistry in ASTM as well. And that's a good way to do it because now you're combining mechanical requirement with chemistry requirement. The same way here on API, if you say I want an API pipe, but in addition, I want the chemistry to contain a certain amount of nickel, for example, that just really builds up your safety level. Now, the welding, a lot of times will end up being part of what we call the project specifications. So it's not on the drawing, but it's still a lot of requirements that you need to follow. If it's a building, for example, they have a lot of templates for those. And it could be a 300-page document that's going to refer to codes and standards and also have some discussion on how to be careful, who's responsible for what. So it goes way beyond the drawing. Now, in that specification, the common thing to do is to refer to specific section of standards as opposed to be calling for your own process specifications. So you try to use something existing so you don't have to generate 160 pages just on how to make the pipe. It's not practical, but the point is if you ask for an API 5L, a lot of times you have to complete that with what is your inspection criteria, what is the grade that you're looking for, are you going to allow for seamless electro-resistance welded, a lot of options that you have to build in. And that should be it with respect to the material. So if you refer to a product specification, and we have plenty, like this fitting, for example, has an ASTM just on it for dimension, for testing that needs to be done on it, for the material to use. Now, there will be options. They'll say, well, in terms of material, I give you 2 or 3 options, so you have to say which one you want. So it's the most prudent approach to call for a standard, but understand that standard so you know what is optional and what is required. Thank you. And speaking of understanding what's required, I mentioned about those pipes that are made from flat and then bent into shape. The standards, the one we're just scrolling through, tells you to test using a circumferential cutout, flatten it, and then do the pull test. Does it make sense? Good question. Maybe we'll all agree here that it makes sense because you are interested in the resistance to a hoop stress. So you're more interested in the expansion resistance of the pipe than you are about the longitudinal properties. The counter side to that is you started from a flat sheet to make that pipe. So you had some cold forming involved on the surfaces. Then you flatten it back, you have more cold forming. So here is a composite response that you're getting from your test from all this forming history and the material itself. Which way is better doesn't really matter in the end because you have to meet the specification. Now, it becomes important because people criticize this technique depending on how you flatten it, depending if you use a lubricated tool or if you just doing it dry, you'll get a different response. You actually get different properties. So there's pressure to move to try to take a longitudinal sample and essentially give you a lower bound, a lower value of that yield strength because now you don't deform it back and forth. But it's one of those things that, again, even if the standard is super thick, it's not perfect. And that's why understanding it is important to any engineer that's going to define it. So I think we've covered the very basic for chemistry and mechanical. And you asked about coatings earlier, and that's a topic I want to briefly cover. The fall has more detail on corrosion. So here we'll just say that when you ask for something galvanized, it could mean very different things. Electro galvanized, these are the fasteners that you can get at Home Depot. They'll work for a few days. They don't rust right away. It's great, but it's a very, very thin coating. There's, of course, a difference in the service life of having these cheap fasteners, the galvanizing that you have on the body of a car, and then what is the hot dip galvanized or sprayed on zinc that is a lot thicker. It comes important in a lot of applications. This is an example of just a screw showing that when you drill the hole, you expose the galvanizing, and that itself leads to some corrosion. The idea is to control that corrosion, but you can use to protect that hole from growing. This is real trouble in the sense that if it's the structural steel to hold the entire cladding for the building. So we have that on Stetacellar, for example, different layers, and then there's one piece holding the other. So if you lose metal around that hole, you lose the thread, everything falls off, no good. What happens here is when it's drilled in place, that's very, very common. So you have self-drilling fasteners, you have your sheet, and you just go wherever you want and install the sheet. So you can use the galvanizing in the vicinity of where the exposed metal is, but that vicinity is of the order of 5 or 6 millimeters for condensation. So in other words, if you're not submerged in water, the cathodic protection effect of the zinc can only go so far. It will only go to the extent of a film or a droplet of water, and that's millimeters. So it's a very good example of application where if you expect a lot of moisture and you're thinking about long-term service, you can't use these thinner electro galvanized samples. And of course, they're a lot of cheaper. And also, if you're looking at bolts, if it's hot dip galvanized, so they're very thick coating, a lot of times it's hard to put the nut on because you built up the thickness, so it's interacting with the thread. So there's a lot of limitation if you had a fastener. And one example is screws for decking. If you have a hot dip galvanized fastener, it's a lot harder to drive it into the wood. It's hard to get a very square head or a Phillips head that will just grab with the tool to put it on. So a lot of times you end up with an hexagonal lugboat type feature if that's what you're specifying. So it becomes important in a lot of cases to think about how you're going to protect it. The chain that I circulated, one big problem with that one was you lose the coating. So it's going to rust there. Now, if it's an application in water, you can use cathodic protection. It's a perfect case to protect the areas that get scratched. A lot of times when you have cathodic protection, by the way, we put that on all the big transmission pipelines. They're coated, and then they have cathodic protection for where the coating breaks. If you didn't put a good coating, you'll use too much current. It will really not be efficient to try to protect bare steel underground. But the idea is during installation, there's going to be some damages, and your coating is not going to be perfect. That's why you use a combination of the coating plus cathodic protection. And that was the case for the storage tanks that we talked about last time as well. It was coated plus cathodic protection. Yes?
Can you explain the cathodic protection?
Sure. Yes, it's hard not to get a little bit into it. So we have the anode and the cathode in corrosion. So let's say that it's iron here. So we have a plate of iron, and we're considering forming a little hole in here. What happens is you get your iron to go into solution, and that's bad. And then you have the recombination reaction that varies. Sometimes you'll so that's the reduction reaction. So you have an oxidation reaction, you have a reduction reaction, and by playing with the potential, you really eliminate this one on this piece of metal. So what happens is you have in the ground another anode. Let's say for an underground storage tank, you have magnesium. So you get the magnesium to get to the magnesium 2+, and then you still have the reaction of forming water or hydrogen here so you eliminate this part altogether. That doesn't happen anymore. And this is the reaction that happens with the reduction taking on the surface right there. So you transfer the action from the iron getting into solution to magnesium going into solution. And the reason it works is this anode is in an electrolyte. So you need to be able to transfer ions through the soil or the water. So it's the only way that you can either have a galvanic corrosion, so that was the other example I was going to show, or cathodic protection is by sharing electrically a path and through the electrolyte. If you have those two conditions, you can put it to your advantage or disadvantage. Yes?
So is that magnesium sacrificial then?
In this case, it's sacrificial. You can have some permanent anodes, carbon-based, that will still have essentially a certain form of ionic reaction on the surface, and make sure that you do not have a reaction of dissolution. Yes. And the problem when you go to a permanent anode is there's a tendency to put a lot of voltage because you're protecting more, and that's where you start forming hydrogen on the steel, so it could be a big disadvantage. So zinc is great, can only get to 0.8 volt of protection. Magnesium can get you to form hydrogen on the surface as well. So the galvanic effect is the exact opposite. Let's say that we have normally the copper here corroding in the environment, what happens is if you put it in touch with steel, the steel gets into solution and you just essentially have a catalyst. The surface of the copper is there trying to corrode, but it's actually corroding the other elements. So the biggest issue with copper is, again, it's a clean surface. It wants to react. And it's more noble than steel. So it's a very big issue if you're putting up a copper roof. That's the easiest example to remember. You don't want to use steel nails or fastener. It's just not going to work. If you have the opposite, if you have a steel roof for some reason, maybe weathered steel, you use copper fastener, that's great because the smallest link and the one that's also not directly exposed to the environment is the most noble. So we use dissimilar metals a lot in construction, but we have always to be careful on which order we are. So the smallest element in general should be the more noble. So using stainless steel, for example, to put together aluminum is great. If you try to do the opposite, you could have a problem. So it's just a question of trying to think ahead what is going to happen long term. Speaking of stainless steel, the word says it's stainless, so it will still corrode under certain conditions. In the ground, it can corrode as fast as regular steel. So what we do about that, the different ways. So this is just flashing, and you have that on some museums, some fancy homes. Stainless steel flashing that because of exposure to the mist from the ocean just starts to pit and corrode. It doesn't really lose thickness, but it definitely loses the appearance. And one way to mitigate it was to put a very thin acrylic base coating on it. And in the context of coating, just very briefly, you can pass those around. In the context of coatings, one advantage with coating a stainless steel, and we do that a lot with fancy stainless structure, is you don't need to protect against the oxygen going into the interface. So if you have steel here and you're trying to coat it, your real issue is to get moisture and oxygen to travel through your coating, because that starts the corrosion. You have spoliation. It's not good. The big advantage with stainless is you're only trying to prevent the chloride to get to the interface, because that's your main enemy to cause the surface corrosion. So you don't need to have as good quality of a coating to protect the stainless steel against corrosion, but a lot of times you do need something if you want to avoid. And it's very hard to mitigate. That's these images here. You start finding these pits, you see the small holes there? So once it's done, you can try to clean it, polish it. If you still have the holes in there, it's never going to be as resistant as it was in the first place. So it's very, very unfortunate. A lot of people don't really think of this issue, but it does come into play a lot. So we started a little late, so I'll have more material on this tomorrow. But I'm happy to talk if anybody stick around for a few minutes. Thank you.